Great, thank you very much. Again, welcome to day 3 of the 7th annual EPRIIA Challenges in Energy Decarbonization Expert Workshop. My name is David Hunter, and it's my pleasure to welcome you to the 3rd and final session of this event. We had a fantastic session yesterday, great participation, great speakers from both sides of the Atlantic. But I think what really made the session great was your participation, the participation from all of you. Let's see. So as Will said, please use the chat function now to introduce yourself. And in fact, I'm going to ask you to do 3 things with the chat function today. So first, again, introduce yourself, name, company, position, where you're from. We want to know who you are, and we want your views. Second, ask questions. Offer comments, offer advice, offer your perspectives throughout the workshop. We would love to hear it. And third, one more thing, different from the other 2 sessions, I'd like to ask you to please suggest topics for future workshops. So this is the 7th annual time we've done this event. We will be doing it again next year. We'd like to know what topics, what additional things you'd like us to cover. So please enter those into the chat. Again, we had a fantastic session yesterday from energy regulators on both sides of the Atlantic. We heard about very different approaches different jurisdictions are taking to create market rules to best manage distributed energy resources. And one of the things that we began to delve into was reliability and resiliency. So we're now going to turn to that topic in greater depth, starting with our poll. So the poll is now open. There are 2 questions. Do distributed energy resources increase or decrease reliability? And then which DER technology has the largest potential to increase resiliency? So those will be open for the next 30 minutes or 25 minutes or so, I guess. So please take a moment to fill those out. As we turn to session 3, reliability in a decentralized system, I note that it's an appropriate day for us to be discussing this topic because across the eastern U.S., where we're hosting this event from EPRI's offices, we're now being hit by the remnants of Hurricane Zeta. This has, in fact, been the most, well, it has been a record-breaking Atlantic hurricane season. We've had 27 named storms, a record of 11 of which made landfall in the contiguous U.S., and currently, I believe, some 2 million people in the southern U.S. are without power. And we're getting storms currently over the 2 main offices hosting this. So if for any reason the webcast does go out, we will be reopening it from a different office, and just please sign back in using the same link. It is now my pleasure to introduce your moderator for session 3, Alejandro Hernandez. Alejandro is the head of the IEA's newly created Renewable Integration and Secure Electricity Unit. Before joining the IEA 3 years ago, he was a leader in energy in Mexican government, including as managing director for analysis and market surveillance in Mexico's Energy Secretariat. I would also like to note that Alejandro has been the IEA's lead organizer for this event for the last few years. It's been a pleasure to work with him. I very much appreciated his knowledge of energy markets, of electricity markets, and his contacts all over the world. So without further ado, Alejandro, over to you.
Thanks so much, David. I'm glad to be the moderator of this 3rd and last session of our workshop. I'm sure that is going to be very interesting. Reliability is a topic that always gets a lot of interest for regulators, of course, from system operators, and from policymakers. But it's also very interesting the fact that the way we treat reliability, it hasn't changed that much over the years. Even if we are witnessing like an amazing technological change in the last few years, if you think where our reliability standards in many of our countries come from, they still come from dark ages from many decades ago, which is interesting. And there are always these kind of interesting questions. So, okay, given the path that the energy system is taking, should we keep this the state of things? Should we give electric vehicles in the future to have the same kind of consideration we have for a household, for heating, for instance. So I think there are plenty of interesting things. The IEA launched last Tuesday a report on electricity security, which is called Power Systems in Transition. So this is a subject that is very dear to us, and basically the message is we need to update our electricity security frameworks in order to take advantage of all the opportunities that are coming. So before I start this, I would, before giving the floor to our first speaker, I would like to ask our speakers to respect the time that was allocated for your presentation. We will keep the questions and the discussion at the end once every speaker has had a chance to speak. And without further ado, I would like to welcome Mr. Daniel Brooks, who is President of Integrated Grid and Energy Systems at EPRI. Daniel is going to speak about grid reliability in a high renewables world. Daniel, the floor is yours.
Thank you, Alejandro. Everyone hear me okay?
Sound great, Daniel.
Okay, all right, great.
Thanks.
All right, perfect. Well, good morning or good afternoon, depending on where you're joining from. Appreciate the opportunity to join such a great discussion. So Alejandro and David asked me to talk about what reliability looks like in a high renewables world, particularly what reliability looks like with a world of high inverter-based renewables, primarily wind, solar, PV. And I want to just give you the big takeaway right up front so that if I lose your attention over the next 10 minutes, you'll have gotten it, because I know you're still with me right now. So really there's three main points that I want to make with the talk. And the first of those is the energy transition that we're all going through. Any pathway that we want to look at to net zero, carbon-free electricity sector, all of those have extremely high levels of renewables, and particularly extremely high levels of inverter-based renewables, solar and wind. Solar and wind provide some interesting challenges to us. That's the second point. They're not like traditional synchronous rotating machines that are dispatchable, so we know that. There are challenges, and so if there are challenges to those types of resources, and we're looking at much higher levels of those resources as we go forward, are there solutions to those challenges? And that's the third point, is there are solutions to those challenges. Many of those solutions we're already aware of. Some of them are already mature, being employed in systems. Others are being developed or conceived of, but we need to be thinking about those and working collaboratively toward those solutions, because those solutions are key to the energy future that we all are looking for and headed towards. So that's the big takeaway. Let's jump in and look at a couple of slides. So if you will, let's go to the next slide. Just want to give you a few insights that sort of drive home those 3 points. And the first one of those is that all pathways for decarbonization of the electricity sector and the broader energy economy, for that matter, all of those lead to much higher levels of renewables, of wind and PV. The analysis that is represented here in the chart that you see in front of you, this is really from modeling that we've done at EPRI very recently, looking at what are the pathways from a technology mix perspective to a zero or to decarbonization pathways in the electricity sector in the U.S., so it is U.S. focused. We'll broaden it out in just a second. But what are the decarbonization pathways for the year 2035? So that's fairly aggressive, a little bit sooner than the 2050 target that a lot of us are looking at. There's a lot of interesting things in that chart that I don't want to take the time to get into. I can answer questions in the chat if you would like, but I really want you just to focus on the green and the yellow. This chart is representing cumulative investments from 2020 to 2035. So these are investments in technology beyond what we have today. So on top of where we're at, so in the U.S., at the end of the second quarter, we had about 110 gigawatts of wind installed. We had about 85 gigawatts of solar PV installed. These are cumulative investments on top of that you see in the green and yellow. And so you're really looking at different scenarios out to 2035 of what those cumulative investments will look like. There's a reference case scenario. There's an 80% decarbonization scenario headed towards net zero in 2050, and then you have net zero, carbon-free, and 100% renewables. And if you look at the additional investments in wind and solar that are going to be required to get to that, you can see the statement that I was making. Any pathway towards deep decarbonization in the 2035 timeframe or even out to 2050, all of those result in significant additional installations of wind and solar PV. So the table over on the left sort of summarizes those. So for the 80% reduction in 2035 or for the net zero, you're looking at about 560 additional gigawatts. So keep in mind the context here. Right now, we have about 195 gigawatts as of the end of the second quarter. So you're talking about 3 times that amount, approximately, that we would have to install over the next 15 years. And if you're talking about a carbon-free or 100% renewable scenario, you're talking about anywhere from 6 to 9 times the amount of wind and PV that we have installed that we'd be looking at. So significantly higher levels of those inverter-based resources that we would have to be considering how to reliably integrate into the system. And even just for a little bit broader context, the total generating capacity in the U.S. today is 1,150 gigawatts, around that. So you're talking about that much additional renewables for the carbon-free or for the 100% renewable scenario, just in renewables, of the entire generation capacity installed in the U.S. today. So significant amount of additional renewables that we're going to have to figure out how to reliably integrate. Broaden out just a second from a global perspective. So BNEF released their new energy outlook a couple of days ago. I'm sure several of you have taken a look at that. But their scenario, which isn't a carbon-free scenario out to 2050, but just from their economics, electrification, generation mix, their analysis, they basically show us going from about 1,500 gigawatts of installed in wind PV globally today out to 12,500 gigawatts in 2050. So whether you're looking at U.S. numbers for decarbonization scenarios or you're looking at just what is being predicted based on economics and policies that are already in place as we go forward, huge amounts of additional wind and PV that are coming into the system. What does that mean for us then as we go to the next slide? What does that mean for us in terms of what we have to think about from a reliability perspective as we go forward? And this slide basically is showing that we know this, that there are challenges associated with integrating additional wind and PV into the system, because the system that we've designed today across the globe in terms of power systems have been based on controlling those systems to take advantage of the physical characteristics of dispatchable synchronous machines. Inverter-based resources, wind, PV, they have incredible control capabilities as well, but we haven't designed our control systems to take advantage of those necessarily at this point. And so what are we going to be looking at? Well, two buckets that I sort of bring to you. One is around variability and uncertainty. That's obvious. The plot that you're looking at here is a plot from earlier this year, a week in the air-grid system in Ireland, so getting a little international flavor there. You see in green is the actual amount of wind in megawatts that you see on the system across that week. You can see the variability, some diurnal variation that you see between day and night. The orange is the instantaneous penetration of renewables in the system. And you see that it gets up to as much as 65%. And hovers for about 4 days between 40 and 65%. EPRIIA actually controls their system to limit the instantaneous penetration to that 65% level because of studies that they've done that show that they have some stability concerns if they go above that. So they have that lever in their toolbox as they're moving towards potential times where they might have as much as 100%. They basically, one of the fixes that they have to the variability uncertainty issue as well as the stability issues, they have to have control of the renewable output. And so I sort of throw, there's over to the right, you see some of the considerations. It affects resource adequacy, variability and uncertainty does. It affects how we do our transmission planning. It affects how we schedule and dispatch, what we think about it in terms of security analysis in real time. But there are solutions to those. One is being able to control the renewables as EnerGrid is doing, limiting that to a certain percentage. Obviously, integrated forecast, accurate forecast is going to be very important. Being able to ensure that we get optimized levels of reserves and methods for doing that are going to be important to allow us to get to those levels, as well as being able to have flexible resources. And that flexibility can come from, other dispatchable resources from generation. It can come from flexible load. It can come from interconnection to other systems that we provide that over. But those are going to be key for us. If we go to the next slide, we'll see that the second sort of set of considerations, which is around the inverter interface to the system relative to the synchronous machine interface that we've had with traditional central station fossil systems. Those also create some potential issues because of the way that we've designed our controls and the way that we protect our system, primarily in that we lose or we displace a lot of inertia from the system. We displace primary frequency control. We displace short circuit from the system that our controls in our existing systems are primarily designed around. And so a lot of potential concerns there, but there are solutions to those. We need validated models. We need to have different controls, both inverter controls as well as system controls, and we need to have provision of grid services from other resources, including things like emerging resources, storage, flexible load, but also from traditional things like synchronous condensers. If we go to the next slide, and I've only got about 30 seconds to wrap up here, you'll have a couple of additional slides for you. There are solutions to these problems, and we have systems already operating at high levels today. This is an example from 2 weeks ago for the South Australia system down in that was provided to us from the Australia Energy Market Operator. You can see that they actually had about 3 or 4 hours where they were operating at 100% instantaneous penetration of renewables, and a significant majority of that was from behind-the-meter PV. A lot of potential issues that you might have with the system for that, as we were talking about, but in Australia, they are already putting some of those mitigation solutions into place with flexible resources, operating reserves, operating forecasts. They have storage. We know about the Tesla battery. They have an additional new interconnector to the New South Wales system that they're putting in place to provide some capabilities. They have synchronous condensers that they put in place. And so there are solutions. And I'll just wrap up. You can move to the next slide, and I'll just give you 10 seconds. But the big takeaway is this. We're going to have much higher levels of inverter-based renewables as we go forward, wind and PV, to accomplish and to achieve the energy future that we want. There are solutions to the challenges that will come, but we need to be working on them now. And we need to be getting those solutions that aren't there in place so that we're ready for them when they come. And you can see as you go through certain levels, certain needs come about as you get to higher penetrations. We need to be working on all those solutions for our energy future as we go forward. So I'll take questions in the chat and turn it back to you, Alejandro.
Thanks so much, Daniel. It's a very, very interesting presentation. We will come back to this for sure in the questions. So let me now cross the Atlantic. This time I'm delighted to introduce Ms. Roisin Quinn, who is head of National Control and Chief Engineer of National Grid Electricity System Operator in Great Britain. She's going to talk about how to keep security of supply using distributed resources. Roisin, the floor is yours.
So I want to kind of,
okay.
Great. So there's a couple of things I want to just kind of draw out, probably give you a taster of some of the work that we're doing in the 10 minutes. I want to just cover a little bit around, leading very much on from Daniel, why do we need to change how we think about system resilience and system reliability, some of the work that we're doing about it, specifically on restoration services, and then just kind of share a few reflections on some of the other work that we're doing with embedded generation and kind of managing that transition. So we just move on to the next slide, please. So what are we doing about it? So where are we at the moment? When we think about moving towards a low carbon system, the system operator in Great Britain, we set ourselves the challenge of being able to operate the power system at zero carbon by 2025. So when the market brings forward that mix of generation that has no carbon, we won't be looking to bring on thermal plants or looking to change that to bring on carbon plants. We are looking now to work out how we would do it with a completely carbon-free system. And one of the things we therefore have to focus on quite a lot is what will restoration services look like? And so we are trying to kind of re-engineer how do we think about that, moving from this kind of top-line world where we have thermal providers providing black start services, centrally controlled by the ESO, and you restart the network kind of from that top-down approach. What we're looking to do is to start bottom-up and say, how would we reimagine all of that so that when, as providers start to exit the market, we can fill that gap. That's what we need to do. But also, how do we take advantage of the opportunities? There's new data services, there's new technology, and kind of all of these new business models we're seeing. How do we take advantage of that to enable us to think about this differently? And what we're doing is we're doing an innovation project. So we're partnered with one of the distribution networks. We are also partnered with a company called TNEI, and as a kind of a partnership between the three of us, we're looking at how do you do this, looking both in terms of what services, what operational models, what telecoms do you need, what power system studies do you have to do to really understand what will this look like, feel like, and actually work, and how does it really kind of happen from the bottom up. So we're looking at technologies, we're looking at communications, we're looking at organizational design, we're looking at resilient telecoms as well as just secure telecom systems. And our ambition is to make sure that these new providers, these new distributed resources, solar, wind, small-scale hydro, can all be part of that wider restoration plan. If we just move on to the next slide, I'll just talk a little bit around what does success look like. What we're trying to do is go bottom up to prove that you can do black start with renewable energy and to break that myth that it has to be big thermal plants that provide those black start restoration services. We think that this will save about 810,000 tons of CO2, so a massive carbon saving in there. And we also think it will reduce costs to consumers by significant millions, because this will allow us to really open up the market and to increase liquidity in the providers who are providing these restoration services. And what we are doing is we are breaking down the component parts of what you would ordinarily get to restore the power system so that other people can provide different parts of it, rather than having to go to that one big thermal unit to get all of it. If I move on to the next slide and just talk a little bit around what have we achieved so far. So the first kind of year and a half of the project has been really understanding what the challenge is. Because it's a very big change, just even the organizational side of it and the process side of it, where you're used to having a strategy and that me and my control room will determine what happens next, what pieces of the puzzle come together in what order. We're now looking at what would that mean if there are lots of different people who are starting up small sections bottom up and bringing them back together. So already we've done an awful lot of the power system studies to understand how you would restore the system and how all of the technical services come together. We've worked through some case studies for live trials. And what we intend to do as part of this project is we're going to demonstrate that you can get the small-scale renewables on the distribution system to self-start, to provide that connection back to the system, and then to start to re-energize the grid from the bottom up. So we're looking to prove that as part of this project. Obviously, before you start doing live trials, with the cost, with the risk to assets, with the impact on consumers, we want to make sure that we know exactly what we're testing. So a huge amount of work has gone into the case studies for those trials. We've also scoped out what the telecommunication change needs to be. So much of our black start service in the UK is dependent on being able to get that immediate connection and those instructions through to the vital power stations. What does that look like when you go to a distributed world? When so many of us are now dependent on Wi-Fi for telephone calls, and the PSTN network is becoming less and less used. I mentioned organizational structures, we're re-looking at them. We're also then looking at what's the preferred commercial structure. Those of us on the project are quite aware we have to first of all prove that it's technically possible. We then have to figure out how you would do it. But then there will be a decision. Is it worth the money for consumers? How much is it going to cost them? Is that the right way to spend their money? So as we're doing this design, we want to be able to use this, and we're very conscious that right now we should be designing in kind of a liquid market, designing in a way to make sure that there are as many participants as possible, really unlocking that value. I want to just kind of focus as well a little bit on what we're doing kind of as our first live trial. So we're starting off with a hydro generator in Scotland, which we're going to island, and then get it to start from islanded mode, and then make sure that it can kind of prove that connection through. We're doing that starting in the next couple of days, in fact. So by the end of this year, we will have done that first trial, and then moving into next year, the focus really moves on to proving what we've been looking at. So we'll be looking to do longer trials, kind of more wider trials, to make that connection up to voltage levels and ultimately get from this small-scale renewable generator all the way back up to that connection point between the transmission system and the distribution system. We are doing, starting to spec out what exactly is needed as well. So making sure that when we think about the various component parts and the telecoms and the technologies, that we are not dictating to the market, you must do these things or you're not part of the journey, but we are setting out quite clearly, these are the requirements that we have that must be met. You can meet them in any way, shape or form that you can, but these are the red lines, the really important things to make sure that we can actually deliver this restoration service from these new technologies. And we're also doing a huge amount of digital simulation. So as Daniel mentioned, how do we redesign control systems to take advantage of the inherent control of different things? We're starting to do an awful lot more digital simulation of that to make sure we really understand all that is possible, but then also the integration of them. We don't want to just look at one thing and say, yes, this works in isolation. We're trying to imagine a power system that is operated in a completely different way, and that integration is really, really key to us. So conscious I've got a few minutes left, so if we just move on to the next slide. I just wanted to share a few reflections on how all of this needs to come together. So we think about 2025 and zero carbon operation in terms of buckets of technical challenges. But we're also quite conscious of how they come together. There's that need to think about do the various codes across the markets that govern the industry in the UK work. So some of you may have seen this summer that we had an emergency grid, change to our grid code to make sure the distribution system operators were able to disconnect embedded generation in an emergency. Now, this is a power that was always set out within the grid code. The system operator always had the right to make that instruction. What we were kind of very conscious of was the scale that we might need to think about that given the impact of COVID. Did that actually flow through across all of the codes? So there's a huge piece of work around what balancing services do you need? How do you make sure you have those grid stabilizing services? But how do you have the right governance structure around the industry to make sure that everything links up? And that integration point that I mentioned, that you don't have kind of pockets of genius, pockets of brilliance, but then fundamentally there's some block or some barrier, some legal impediment to that coming together. We're launching a range of new services at the moment. One is called dynamic containment, which is very much looking at how do you have a faster acting response service, which recognizes in a lower inertia system, you need to have something faster to contain the frequency in the event of a loss. So this just shows you some of the wider work that we're doing to make sure that we are accessing the full potential of distribution resources as we think about zero carbon operation. I'm probably going to pause there. I think I'm just coming in on time. I'm going to hand back to Alejandro and look forward to any questions in the chat function.
Thanks so much, Roisin. It's a very, very interesting presentation. We know that there are many technologies that have capabilities that are not used, and it's fantastic to be able to see these projects that actually are really taking this from theory to practice, I would say. So we wish you the best of luck in your first trial that will take in a few days. I think the next in the agenda, if I'm not wrong, is Mr. Rob Chapman, right?
Good morning, Alejandro. Can you hear me? This is Rob Chapman, and I'm going to go at this a little bit differently. I don't have slides to share with the group, but I did want to emphasize a few points that I think are very important that have come out in the previous presentations. But I'm going to specifically focus on the opportunity around electrification of transport and the opportunity that it offers for the electricity sector to not only enable improved reliability or support reliability, but then also separate from that, its role in ultimately supporting resiliency strategy going forward. And I really want to start by separating those two terms at the outset. When David Hunter kicked off the webcast this morning, he talked about the hurricane that is passing over the D.C. area, potentially impacting the reliability of service in that area. And when we talk about reliability, obviously it looks at near-term, shorter duration events. You expand that to resiliency, and you're typically looking at extreme events that have a significant long-duration impact on our ability to provide electricity to our customers. And one of the things that we really emphasize at EPRI is to begin to think about, not only as we look at decarbonization of the electricity sector, but the other side of that coin is recognizing that we have existing climate vulnerabilities that are beginning to impact our ability to enable resiliency strategies going forward. And so to the degree that we are creating a greater dependence on electricity through electrification of end use and decarbonization strategies, we have this obligation, of course, to ensure that not only are we going to be reliable, but that we think about a more resilient energy infrastructure that can support these longer-term events, whether they be wildfires, hurricanes, the polar vortexes, the heat waves, drought, et cetera. So really factoring that in. And I'm going to specifically talk about the role of transport potentially in being able to provide support in terms of not only enabling the reliability, but then also enabling resiliency. And I love the topic of, or the title that I was given here, competing or complementary in terms of vehicle electrification. And I'm going to answer that up front by saying yes and yes, and it depends. And I'll dive a little bit deeper into that as I provide my remarks over the next several minutes. But I wanted to start by talking about decarbonization in general. And obviously, throughout the globe, decarbonization of the electricity sector is a priority. And we are seeing that perhaps accelerate as some of the technologies Daniel talked about are beginning to become more economic, and adoption of those technologies is leading to an acceleration in terms of decarbonization of the electricity sector. One data point that we cite in the United States is the electricity sector carbon footprint is below that of the transportation sector. So when we look at the opportunity not only to green the fleet of the electricity sector, it's what do we have the opportunity to do in other sectors of the economy. And transport rises to the top in terms of being able to electrify transport and support decarbonization of that particular sector. And then that's not exclusive of what we're doing on the building side or in industry. But just to give you a data point to start, when you think about electrification strategies going forward, and this is a U.S.-specific data point, but currently, right now, electricity makes up about 20% of final energy in the United States. Over the next 30 years, we project that to be around 60% of final energy, a threefold increase over what we are currently doing today. And as I said, with that increased electrification, dependence on electricity, comes an obligation to make sure that not only are we reliable, but we are resilient and supporting that need going forward. When we begin to look at the transport side, I just want to give you a couple stats that I think begin to frame this opportunity that gets folks excited about maybe what mobile storage being the batteries in vehicles, what it might enable in terms of supporting reliability as well as resiliency going forward. Just a few U.S. data points around transport. There's about 250 million light-duty vehicles in the United States today. Over the next 10 years, by 2030, we expect 4 in 10 or 40% new car sales to be electric in the United States. That's being driven by some policy. California, for instance, has new policies around electrification of transport. It's also being driven by economics. When we look at total cost of operation, the opportunity to acquire an electric vehicle today and have it be economically equivalent to an internal combustion engine has never been greater. And if we factor in operations and maintenance and the cost of fuel over the life of that vehicle, typically 11 years or so, the total cost of operation on an electric vehicle is currently at parity with an internal combustion engine. So we expect to see the electric transportation sector grow significantly over the next 10 years. And if I go out even a little further and look over the next 25 years out to 2045, we're expecting about 75% of the light-duty vehicles to be electric. So just to give you a data point, if I take 250 million vehicles, I take 75% of those and I say they're electric, I look at the battery packs in those vehicles and assume a 4-hour storage, we're talking about 2,000 gigawatts approximately of battery storage. That's a significant amount of untapped resources. So let me overlay the other side of this, which gets folks excited. The typical vehicle in the United States is used only 5% of the time. 95% of the time, it is sitting idle either in the driveway of a home, in the street, parked, or in the parking lot at someone's place of employment. So you have an asset that's being underutilized right now. And the typical driver uses that vehicle or that battery only about 10 to 15% of its total capacity per day. Average driver drives 30 miles, so that means that there's about 85 to 90% of the battery storage available on average per day in each of those vehicles that can be used for other purposes. And I think it's very important to note that, once again, from a reliability perspective, those vehicles could ultimately support ancillary services to the utilities and provide frequency control and other services. But when you look beyond that and you look at resiliency, a longer-term duration event, being able to leverage these resources and either support your home, your business, or provide that back to the grid, that battery or that power back to the grid, is once again where folks see the opportunity. Now, that's the technical potential that I like to say. That is what we see as an engineering group. We see this potential. We get excited by it. But the reality is consumers and ultimately what is achievable is a completely different set of equations. And I think it's important that when we look at this that we need to be able to factor in a consumer behavior into whether or not they would be interested in allowing their vehicle to serve as a resource for the electricity sector in order to support reliability and resiliency. That's one aspect. The second aspect is the OEMs. What is the OEM who has warranties around that particular battery pack in that vehicle? What is their expectation in terms of being able to make sure that that asset is being properly managed? And, of course, they're going to have a vested interest. My point in bringing that out, if a consumer is going to be interested in enabling, leveraging this resource, their vehicles, and if the OEM is going to be interested in potentially allowing their battery packs to be used to support the electricity sector, there's got to be some economic benefit to them. And those economic benefits will need to be played out over time in order to support the adoption of this particular concept of a vehicle to grid or vehicle to building, vehicle to house, et cetera. And the last point I want to make is I've made most of my comments around light-duty vehicles, but I did want to mention that we have to think about electrification of transport beyond the typical residential consumer and look at fleet electrification going forward. Everyone's familiar with Amazon. I joke Amazon is daily, shows up daily at my house these days. And in fact, when you look at the growth in that size of vehicle, those vehicles on the road have grown by 3.5 times over the past 10 years. And that's that smaller Class 2, Class 3 delivery van that Amazon, UPS, and others are using, what we call last mile delivery. When Amazon thinks about resiliency, they think about 24/7. That vehicle needs to be available 24/7. If I think about electrification of public transport, that also needs to be available 24/7. There's not time for those vehicles to be out of power or to be providing services back to the grid, typically. And so when we think about resiliency, we also have to think about which customer segment we are serving as we talk about being able to provide resiliency services, whether that be vehicle to grid or other options that we look at going forward. And the final point I'll make is that we also have this option around being able to leverage these assets and control when they are charging. Managed charging being different than vehicle to grid. It's a one-way signal that utilizes the charging capabilities when it is best appropriate or a best fit for the utility in terms of events that are going on. Managed charging, which is separate than vehicle to grid, offers us a great opportunity within the industry to be able to support reliability in some resiliency scenarios. And it is something that I want to make sure that we don't overlook as we think about the opportunity that transport offers. So Alejandro, let me turn it back to you. Look forward to addressing any questions in the chat or in the dialogue that ensues. Thank you. Alejandro?
Thanks so much, Rob. Was a very, very interesting presentation. At the IAA, we speak every day basically on what will be the impact or how we will be able to use electric vehicles and how they will be able to interact with the grid. So it's one of the points we discuss the most in these days. Thanks so much for your presentation. So now from the US, we are going to cross the Pacific Ocean all the way to Australia. Our speaker is Barry O'Connell, who is Principal Engineer in Future Energy Systems in the Australian System Operator, IMO. Well, given the fact that we were very interested in having an Australian perspective today, and that this is 2 a.m. in the morning in Melbourne, Barry proposed to make a recorded presentation. And we are very happy to have it here. He said, by the way, that he's very happy to answer all the questions that we may gather. You can send it to us, and he will answer back. So, with no further ado, Katie, please.
Hello, everybody. Welcome to this presentation on integrating distributed energy resources in Australia's largest electricity power system, the National Electricity Market on the east coast of Australia. My name is Barry O'Connell and I work in the Future Energy Systems team in AEMO, mainly focused on the security challenges with operating the system at higher levels of renewable penetration over the coming 5 years. A little bit about Australian Energy Market Operator. So AEMO is the independent system operator and also the market operator for both the national electricity market, which is on the east coast of Australia, and also the wholesale electricity market, which serves the west coast of Australia. We also operate the retail and wholesale gas markets across the southeast of Australia and Victoria's gas pipeline grid. So shown on the left-hand side of this slide is a zoomed-in version of the national electricity market, which serves the east coast. Up the top we've got Queensland, the capital city is Brisbane. We can see on the table on the right hand side here that Queensland operated 14% of its energy from renewables in 2019. And it has a state target of 50% renewables by 2030 and all states have net zero by 2050. New South Wales in the middle, where the capital is Sydney, operated with 17% of its energy coming from renewables in 2019. And in order to meet its net zero by 2050, it will have to reach about 50% of its energy by 2030. Victoria, which is down the bottom, the capital city is Melbourne, that's where I am based at the moment, and it operated with 25% of its electricity from renewables in 2019. In 2030, it's aiming for 50% and again net zero by 2050. South Australia, which is shown on the left-hand side of this map, the capital city is Adelaide, a world-leading power system for renewable penetration. They've operated 53% in 2019, mostly wind and solar generation. They plan on being 100% powered by renewables by 2030. The Tasmanian power system, which is also really interesting and world-leading power system in its own right, has operated with 95% of its electricity supplied by renewables, the majority of which has been hydro, and it's aiming to have 200% supply of renewable energy by 2040. IMO's integrated system plan is a whole of system plan which provides a roadmap for the efficient development of the east coast of Australia for the next 20 years. A graphic from this report is shown on the right hand side where we can see on the y-axis or the vertical axis the install capacities of renewables and storage in the NEM. On the x-axis we can see the years. So on the left hand side here we can see the actual installed capacities of renewables and storage in the NEM. And just to note, last year 2019 at the end we had 9 gigawatts of rooftop solar installed on the east coast, the majority of which over 90% was installed on people's roofs, which had a penetration rate of 1 in every 4 households on the east coast of Australia had rooftop solar installed. When we look out to 2025, we can see in the central scenario in the integrated system plan, this 9 gigawatts could increase to 12 gigawatts. And in the step change scenario, that this could increase to 18 gigawatts by 2025. Based on this year's install rates, we're tracking closer to the 18 gigawatts, the step change scenario, than the central scenario, but it's definitely a watching brief over the coming years. So taking a look at the renewable integration study, which stage 1 was published in April of 2020. The renewable integration study builds on the integrated system plan, but focuses on the security challenges around operating the system with increasing penetrations of wind and solar out to 2025. The graphic on the right hand side shows the penetrations of rooftop solar. On the y-axis here we can see underlying demand for the east coast of Australia. So the underlying demand goes from anywhere from just above 15 gigawatts up to 35 gigawatts peak in summertime when we have a lot of air conditioning load on those really hot days. On the x-axis we can see the percentage penetration of rooftop solar. The different dots on this graphic, so the grey dots represent every half an hour period for the year 2019, so last year. And we can see the very right hand side of those grey dots just touches 25%. So 25% of the electricity on the east coast of Australia during those half hour periods was being supplied by rooftop solar. If we look at the ISP projections, which we saw on the previous page, the red dots show the central scenario from the integrated system plan, so that 12 gigawatts of build, and we can see with that increased build of rooftop solar, the penetration increases from 25% out to about 35%. And as we're currently tracking on the step change scenario, we can see on the orange dots, this is every half an hour period for 2025 based on that step change build. And we could see that at times we could be operating the east coast of Australia with 50% supply from rooftop solar. So in order to understand how this world-leading penetration of distributed solar PV is affecting or challenging the operation of the power system, we need to zoom into a state level. On the right hand side here we can see the 5 states which I spoke about earlier. So at the top we have South Australia, which has the highest penetration of distributed solar PV, and last year operated with 66% for a single half an hour period of its energy coming from rooftop solar. Since then, only last weekend, we have operated the power system at 77% of its electricity for a single half an hour period from rooftop solar. Victoria, which is next on this, we can see that, and Queensland have operated with up to 30% of their electricity for a single half an hour period being supplied by rooftop solar. New South Wales, which is just under 20%, and Tasmania, which is less than that again, which is around 15% penetration. Also, what you can see on this graphic are some colored zones. These represent the different challenges which are faced by when operating the bulk power system as penetrations increase. So zone A, the yellow zone, is when we start going above 20% penetration, we see a noticeable impact on the load profile. This affects, firstly, our emergency scheme, so emergency under frequency load shedding. So in the event of an extreme event, we have safeguards in place which would balance the power system if we lost 2 or 3 generators for a freak event, and we would disconnect customers at the same time in order to preserve the whole power system from toppling over. As you put more and more distributed solar on these feeders, disconnecting these is less effective at protecting us for extreme events. Also, as we go in above this, when we get into other extreme events, like some of the ones that we've had in Australia over the past 12 months, which are bushfires carving up parts of the network, and the lowering demand due to the pandemic, being able to actually dispatch this generation and having visibility of it starts to become challenging, and it's a really important lever when we want to secure the power system and balance it. So recommendations coming out of the Renewable Integration Study really are around improving our UFLS schemes and reassessing them, and secondly, adding that level of curtailability and visibility on these devices to be able to balance the system going into the future. Zone B, shown here, is the blue zone, and kind of starts to kick in when we go above 30%. And really, this is from our experience with operating the system with the current PV fleet, but what we see is during disturbances on the grid, so lightning strikes on the grid, we see some fall off of distributed solar PV for those events. This increases the challenge with keeping the power system secure, and really we would like them to stay connected to the power system when these events happen, much like large-scale generation are required to stay connected to the system. The work we're doing there is on improving the performance standards and getting validation to make sure that these devices support the secure operation of the power system, especially as it becomes the majority provider of power to the system over the coming years during certain periods. I suppose the last piece on this is the gray zone, and this really is showing where we need a minimum number of large synchronous machines on the system. So the power system in Australia and most power systems around the world need a minimum number of synchronous machines online to keep the system secure. As we start to go into these penetration levels above 75%, we can see that we no longer have enough demand available to keep that generation online, and it's challenging how we operate the power system securely. I suppose really in order to be able to operate the system at higher penetrations into this zone, we would need to reduce our reliance on a synchronous machine, which we could replace the services that they provide from non-energy providing services such as synchronous condensers or batteries to be able to operate out into that zone. Just lastly, I'd like to talk a little bit about our record-breaking day for solar in South Australia last weekend. So what we can see here is that during the middle of the day, 100% of the electricity in the state of South Australia was supplied by solar, and 77% of that was from rooftop solar PV on people's houses. We can see here the blue is gas generation, and that was being exported to the neighbouring state Victoria at the time of this record breaking. And just to say, if you want any more information on the Australian energy transition, there's a lot of material available on the AEMO website and some really detailed webinars explaining a lot of this stuff. And because it's the middle of the night in Australia, if you've got any questions or clarifications or want to know more, I'd encourage you to email the Future Energy inbox, so futureenergy@aemo.com.au. Thank you very much for taking the time to listen to this presentation, and I hope to hear from you soon.
Perfect. Then I will briefly introduce to Amro Farid. Amro is a professor in Dartmouth College, and today he's going to speak on cybersecurity and resilience. Amro is a very close friend to the IEA. He's always coming with a very interesting insights, and this is really his topic. Amro, the floor is yours.
Okay, thank you, Alejandro. Are the slides going to go up in a moment?
They're coming up now.
I'm waiting for the slides to come up. Okay, great. Thank you. I'd like to thank the IEA and EPRI for allowing me to speak about cybersecurity and resilience today. Next slide. Next slide, please. Thank you. And the goal of our presentation today is to give an even-handed woods from the trees perspective on the cyber-physical resilience of the electric power grid, despite having about 10 minutes, and that this is a very active and noisy space, which, in my opinion, is oftentimes prone to sensationalism. I'll leave you with my bottom line up front, in that we oftentimes think about cybersecurity of the grid, and what we really need to do is evolve our paradigm towards cyber-physical resilience with innovations in grid technologies, markets, and policies. Next slide, please. So speaking of sensationalism, I'd like to highlight a couple of very well-known cyber attacks. So in 2007, in Idaho National Laboratories, there was the Aurora generator test, where 30 lines of code were used to manipulate a breaker on a 27-ton generator and basically caused it to very spectacularly fail. You can go onto YouTube and watch the video for that. Another famous attack was the Stuxnet centrifuge, which was really between the United States and Israel, where they took advantage of a Microsoft vulnerability in a Siemens PLC to disable the centrifuges as part of Iran's nuclear program. And then in 2015, Russia was able to deploy crash override as a malware to a substation in the Ukraine, which created a blackout for a period of an hour, which really shows more of capability rather than the actual attack itself. I think many of us could have interpreted that as a warning. So the anecdotal evidence indicates that there's a severity of the problem, but it's not really quite enough. Next slide, please. If you were to look at the grid holistically, you would find that we, of course, have our supply chain of generation, transmission, distribution. All of those different assets are going to have different types of cyber interfaces, and then they're going to be on different types of networks that are very heterogeneous in nature, and then they're going to be talking to electricity markets, service providers, customers, and operations through the internet and other forms of networks. And this picture, which is, really, the simplest mentality you can have to it is Swiss cheese, is only going to grow in terms of cyber interfaces as we end up including the energy Internet of Things. We have written a book on the energy Internet of Things, which kind of goes over the space, and particularly as we deploy Alexas and electric vehicles and all of that, there's just much more opportunity for the vulnerability of different types of devices. Next slide. So that leads you to think, well, we have a really daunting problem. How are we going to manage the cybersecurity of all of these different devices that have different communications interfaces? And what popped up over the last 10 years is a number of cybersecurity frameworks. I've sort of melded my own from a number of different papers here that look at the different types of components, whether they're cyber, physical, and then, of course, there are different types of threats. What are the source of the threat? What is the target application? What's the motive? What's the attack vector? You could be trying to have a denial of service attack. You can be also, introducing, faulty data. The consequences can be of various types. Are you trying to bring about, compromised privacy or integrity or availability? The vulnerabilities also have lots of different causes as well, and different types as well, whether they're cyber, physical, and physical. You can characterize an attack by multiple features, and there could be preconditions like insider knowledge, the attacked element, maybe it's a pump, the method, how are you going to gain access, what is the influence, the affected element, and then the resulting impact. And then if you recognize this sort of, vulnerability as a whole, you can say, well, I'm going to defend it with a number of different things. So the first thing you want to be thinking about is protection so that it never happens in the first place. And then there's intrusion detection, steps that you're going to take while it's actually happening to, to act as a very defensive approach. And then mitigation is the last step. And so this causes you to really think, well, what am I going to do, and could I potentially, save, every single component and protect every single component that has these interfaces in the grid? And chances are the answer is no. So next slide, please. And we really must be quite practical in our approach. And the way I demonstrate this is from a hypothetical conversation between a power systems engineer and a cybersecurity scientist, where, one is going to be more skeptical and one is enthusiastic. So, you can have a shotgun test where a power systems engineer says, but is all of this any worse than a disgruntled customer one day getting their shotgun and shooting at the local substation? And they might respond by saying that the cyber attacker can take out the substation, as we've seen, without detection or being apprehended. And then the power systems engineer might reply and say, well, I have this thing called N-1 contingency analysis, where I'm ready for the loss of a 1.5 gigawatt nuclear generator, or I'm ready for a 2 gigawatt tie line as my largest contingencies. How might you respond? The cyber attacker doesn't need to take out the largest contingency. They can take out multiple coordinated facilities simultaneously, and there are methods in the literature that are developing that we might call N-X contingency analysis. So what about stability? As we know as power systems engineers, there's frequency voltage stability analyses, and here, the cybersecurity scientist is rarely trained in evaluating grid stability, and so the methods that tie cybersecurity to the stability of the grid are not necessarily tied. So what about reliability measures? We might look at, expected LOLE, LOLP, the safety measures, and then, but maybe those measures are a bit too rigid because the cybersecurity person might say it's pretty difficult to quantify these measures when new threats are being devised all the time and their probabilities are known. This is, what we could call a wicked problem where we have unknown unknowns, right? And then there's market stability. So what does this mean for the stability of the grid's markets and services? And here we recognize, and there's a substantial literature on this, that they are a target. Some market designs are structurally better than others. And really the threat of the severity is still unknown. So hopefully what this conversation, this hypothetical conversation shows is that you want to have an integrated threat severity assessment that is multidisciplinary in nature and brings together these different perspectives from different types of stakeholders in the grid. Next slide, please. one of the things that we can see optimistically is that a resilience mindset is actually tied into both a power systems engineer way of thinking and also a cybersecurity scientist. So when we think about in power systems engineering, let's say a nuclear power plant going down or any other large facility, we can, we know that there's going to be a frequency deviation, and then there are various levers of operating reserves and different types of controls that will bring us back to normal, and we're ready for that. And utilities also think the same way when a storm comes, whether it's a snowstorm or a hurricane or otherwise. In the meantime, a cybersecurity scientist doesn't try to, protect the castle all with one wall, one firewall, but rather there are layers of security, knowing that the outer layers will eventually come to breach, particularly with a sophisticated adversary, and that we want to have more and more layers, and that the, quote unquote, the crown treasure or jewels are very much on the inside. So we recognize that blackouts will happen, components will fail, and what's most important is how we survive them, respond, and learn. Next slide, please. So, and then I'd like to leave you with my last insight in that we have developed the Electric Power Enterprise Control System Simulator as part of our techno-economic analyses for variable renewable energy integration. We applied it with ISO New England, and when you have a simulation that looks at the physical power grid with the automatic generation control and multiple layers of markets, you can begin to see holistic behavior that is not apparent from just one market or one controller or the physical grid on its own. And on the right here, what we show is that small changes in the information between the markets and the physical grid and the generation can actually lead to system-wide instabilities that you would not have seen if you had only studied just the market or just the controller or just the grid on its own. And so we really must be evolving our thinking from hacking individual components to system-wide stability where information is an important part of that system. Next slide, please. So I'd like to leave you with some of these take-home points. The electric power grid has already suffered debilitating cyber attacks from highly sophisticated adversaries, and the severity and sophistication is only expected to grow. As the largest machine ever built, the electric power grid presents a daunting, ever-growing attack surface of cyber and cyber-physical interfaces. In order to cope with the unprecedented complexity, cybersecurity frameworks composed of taxonomies of components, threats, vulnerabilities, attacks, and defenses are being developed. The cybersecurity paradigm of security for every cyber interface must converge with a practical physical security paradigm. Fifth, blackouts happen, and how we survive them, respond, and learn is what is important. And then, much like VRE integration, dynamic and holistic approaches are necessary to objectively assess severity and design mitigating solutions. So we want to go from, a purely cybersecurity mentality to a cyber-physical resilience mentality where we're going to have to make innovations in grid technologies, markets, and policies as we go along. Next slide, please. And I would, since these slides are going to be shared, I wanted to leave you with about 20 references or so. In my opinion, these are some of the best references on the topic, so if you do continue to research on your own, this is a great place to start. Thank you again to the IEA and EPRI.
Thanks so much, Amro. This is a fantastic presentation. This is really one of the topics, I think, at least from the policy arena, is one of those that are the less understood. So at least for me, putting the cyber-physical dimension in context, I think it was already a very enlightening, insightful term. So for me, that's very good on that. So propose to the audience, go to our websites. You will find this presentation, and you will be able to find various presentations as well. So I encourage you to watch it because it's really good. And now I think we're going to take some questions, and I'm going to start. I think one question that could be either for Daniel or Roisin or both. And the question is, like, very often we hear on inertia, like one of these kind of obstacles that we hear that, okay, you cannot go to large shares of renewables because they don't behave like that. No, these inverter-based resources, they are not. But now I hear the system operator in the Great Britain saying, well, we want to be able to do it in very few years, by the way. So are we overstating the risk that inertia is to lack of inertia, I would say, to the system? Or are we giving the proper importance to this? What are we missing here?
I can jump in, and then Rosen, you can clean up and get everything correct for me. So I think a lot of times, Alejandro, when people talk about inertia being a limiting factor, they're not really power systems engineers that understand what inertia is and how it actually contributes to operational reliability. I think a lot of times they're thinking of the overall context of what you're missing with dispatchable synchronous machine generation. But just taking the question as it is in terms of inertia, inertia obviously, it's one of those characteristics of synchronous machines that we've taken advantage of in terms of the way we've designed the control of the system to operate reliably, right? What does inertia do for us? Well, whenever we have a disturbance on the system, inertia basically provides us with that instantaneous response that helps to support system frequency, and it arrests or it minimizes the actual rate of decay of frequency when you have that event, right? Are there other ways that you can actually get that same reliability contribution as you're trying to manage frequency? Absolutely, you can do that, right? You can have very fast, instantaneous injection of megawatts into the system that can also provide that limit or reduce that rate of decay or that initial rate of decay of frequency until you can get secondary frequency control systems that help bring the frequency back. And so your question is, are we overstating the importance of inertia? I don't think we're overstating the importance of inertia. It's critical to the way we actually operate our systems today. But the real question is, for the systems that we're going to be having as we go forward, are there different control approaches that we can take to provide that same operational reliability? And the answer to that is definitely yes. There are opportunities to use both inverter-based wind PV, but also other resources to provide that same type of frequency control that provides the operational stability that we want. So I'll stop there and let Rosen help with that.
You're muted, Rosen.
There we go. Great. So I was just agreeing with Daniel. So we absolutely do need inertia. The question is, where else and how else can you get it, rather than just thinking about spinning plants? So if we look back at this summer and how we operated a power system in Great Britain, we took a huge number of actions at real time to change the output of what the market would have brought forward, far, far more than we ordinarily would. And that was to make sure that these really low demands that we were seeing with these really high output of solar and wind, that we had enough inertia. And this summer, we ran thermal plants to do that. By 2025, we want to do two things. We want to have 0 megawatt solutions for inertia. And we're running a number of innovation projects, our stability pathfind, as we call them, to find different ways to do that, to kind of to break the product down into different pieces. And we're also looking at a completely new suite of frequency containment services. The first one of them, we're calling dynamic containment, operates real quick. It is effectively a near instantaneous injection of megawatts into the system. But we're also then backing that up with a whole kind of rethinking frequency response. Exactly that. How do you think about the controls? How do you think the speed? So we're tackling the problem from two sides. What does a synthetic or a different inertia look like? With that, how do you need to contain the frequency, and what fast acting services do you need? It's not that inertia is not important. It's that we're looking for different ways to get it, and we're not locking ourselves into the technology of the past, but are thinking, what does it look like in the future? What is out there, and how do we make use of that?
Thanks so much, Daniel. Thanks so much, Rosie. I'm going to take one. I think I will give it to the speaker that chooses one, or maybe all of you. We have a question from Adria Brooks. If you could choose one technology, now that we're speaking about the stimulus packages, if you could choose one technology that should be supported or should be improved, or you should spend some money there, that could, on a distributed resource, and that could improve resilience or reliability, which one would you choose? And I think all of you would ask an answer for all of you.
So if I'll start, I probably wouldn't call it a technology, actually. What I really think would help the grid the most is actually real-time markets at the retail level. If we're able to have price incentivized, flexible demand at the grid's periphery, then all of the devices that are going to come onto the market in one way or another are going to be that much more synergistic with the grid. So that's some innovation in market and policy.
Thanks, Amro. Someone else?
I think my answer is probably very similar. I was thinking about integration. The challenge is not a particular technology; it's how it works together. How do we simulate that? How do we learn quicker than the market and the power system changes? And the challenge isn't really just a single technology in isolation. It's this new mix of market, this new mix of technology, this new mix of business models and consumer expectations. That integration piece and how we stimulate that and stimulate that is probably where I think there's most to go at.
Yeah, I would echo that point. I think the data capture, data curation, the analytics that goes with that to help accelerate I guess, meaningful decisions and how to operate the grid more effectively with all of these distributed energy resources is key. And then I also do agree with the dynamic pricing comment also, to the extent that we can influence behaviors and provide proper signals, pricing signals is going to be incredibly important.
I'll jump in and throw my nerdy modeler answer in, because all of those things eventually have to find their way into how you model and plan the system, right? So I think we have to understand how those individual resources can perform, be able to characterize the performance based on new market structures, based on the integration, based on the data. You have to characterize those in models that allow you to actually plan and make optimal investments in the system to ensure that you get reliability across supply, delivery, and the customer side. And that's just not the way we plan systems historically. We've got to get to that point.
Thanks. Thanks, Daniel. Okay, so I'm going to our next question. This one would be for Rob. And I think you already kind of hinted a bit. So my question is like, okay, we will have a lot of EVs later in the system, and they might interact or not, but how, when you think now how the consumer behaves regarding using the car, it's very price sensitive. No, you really want to save, to look for a few cents cheaper gasoline, and you might choose the best gas station for that. So you're quite conscious on that. But the same consumer comes back home and basically is completely unresponsive in the saying, okay, if it is in the night, if it is in the day, and for sure it's not taking account if there is a lot of wind at that moment or not. So the consumer of the future, how will behave? It will behave more like the electricity consumer nowadays, which is completely unresponsive, or it will behave as the gasoline consumer of the future, in which is really looking for the best option and the best gas station. What is your take?
Yeah, great question. So my take is, Alejandro, you said it very well. When I go to a gas station, very dynamic pricing at a gas station, depending upon what might have happened that day. Gas prices can fluctuate hourly and provide me a price point that I might either find acceptable or unacceptable to fuel my car at that point. We don't do that within the electricity markets by and large, at least in the U.S. today. We look at electricity, it's relatively inexpensive, and other than time of use rates, we don't really have dynamic pricing signals that send a clear message to a consumer as to whether or not he or she would like to take advantage of that opportunity to fuel their vehicle at that point in time. Transitioning to a dynamic pricing model, very similar to what occurs at gas stations today, would benefit the consumer in being able to make that decision and benefit the utility in terms of being able to drive appropriate behavior. So I do think that it comes back to a dynamic pricing model, that the consumer has to be rewarded for their behaviors from an economic perspective in order to make a decision around supporting, say, grid reliability or grid resiliency opportunities. So dynamic pricing market signals are going to be incredibly important to drive those behaviors going forward.
Thanks. Okay, this one I might ask it to Andrew and someone else, at least one other question. This one is, I really love the discussion that Andrew showed between the power system engineer and the cybersecurity specialist and how they are trying to understand each other. And I think there is something behind, and this is not only common to cybersecurity. I think it's often to the question of resilience. And I think we understand well reliability. We might not know where reliability standards come from, but in some systems, but we kind of understand how this works. I have the impression that still when we talk about putting some benefit on resilience, I think we're still having a hard time to put a number. No? And often we tend to think that more resilient systems somehow one in which we spend more money putting underground wires on the distribution network. And maybe it is the case, but I'm not sure if we are putting the right numbers here. How are we in this aspect? No, are we putting the right benefits here? Are we do we have some good way to measure these kind of investments?
Yeah, that's a great question. You know, one of the things that I oftentimes encourage my colleagues to think about when we use the word resilience is first you have to ask yourself, what is resilience? Well, it's the response of a system to measured with regards to a certain level of performance after some form of disruption. So when you say benefits, well, you have to say what type of performance are you interested in? Is it the availability of certain capacity? Are you measuring from an energy perspective? Are you measuring from a frequency perspective, as I've spoken about? So there are a lot of different performance measures that you could be interested in with regards to resilience. Resilience is not one word. It really depends upon the measure of performance. And then the other thing you have to do is you have to say, well, what type of disruption am I interested in? Are we talking about hurricanes, wildfires, snowstorms, cyber attacks, or otherwise? So unless you start really characterizing that space of disruptions and performance, you're kind of, at the end of the day, hand waving. So.
Thanks. Rushing, any thoughts? Do you have a hard time justifying investments and things that you and your colleagues think that can bring a more resilient system, but actually putting some numbers behind on these projects?
So I think that comment around how the power system engineer and the cyber engineer understand each other. I would say how the power system engineer and anyone else understand each other. A huge amount of our work at the moment is trying to really explain clearly what it is that we're trying to solve and make sure that people understand what part of that problem they can help with. And when we can do that really well, then people are happy to support the investment. They're happy because they can understand the benefit and they can see what that benefit to consumers is. But if they don't understand the why and they don't understand those, if we just kind of blind people with jargon, good technical details jargon, but jargon nonetheless, it's very difficult to have that real conversation about it. Exactly as Amra was saying around what is the risk and how do you characterize that and how do you quantify how often that happens? We spend a lot of time with the regulator and with government trying to work out what's the, the 1 in N of this happening. Is it a 30-year event? Is it a 1 in 10-year event? And kind of my feeling would be everybody's happy with statistics until they are that one. And then suddenly everyone's like, well, that wasn't quite what I signed up to, or I didn't quite understand it. So I think there's a lot of work that we're doing around trying to explain to people the intent of things, the consequences, how you should interpret stats and probability in terms of the impact on the consumer in their home today. What we found as well this summer is that an awful lot of the modelling and the understanding and kind of the agreement, shall we say, in policy has been tested in COVID. A loss of supply event when people are in the office is one thing. A loss of supply event when people are in the middle of a lockdown, their lives have been turned upside down, and they're trying to homeschool at the same time is one more stress that society really just doesn't need. And that kind of how do you feed that into your calculations around loss of load? So a huge amount of work done that we do to try and explain the intent of our work, what the problem we're trying to solve, and then go through the efficiency test so consumers can really feel they're getting value for money, even if they don't understand everything that we're doing.
Thanks so much. We are about to close. I think I will give a try to our last question. This is from our friend Mike Hogan in the chat, and he's asking, I'm not sure if it is directed to someone in particular, can you provide a status report on the commercialization of grid-forming inverters? I don't know if anyone in the panel wants to take this one.
I'll jump in and give a less than complete response, but a response nonetheless. So if you actually contact any number of commercial inverter manufacturers today, many of them will tell you that they have grid forming capabilities that they can enable for their inverters. If you're actually asking how many bulk system grid forming inverter control capabilities are there operating in systems around the world, that's a much lower number. Michael, I'm not sure I could get some information from my team to know, but there's still a lot of questions around how to integrate that grid forming inverter capability with the more traditional system controls that we have, and it's still not. It's the exception rather than the rule. Where you will find them and where there are those capabilities currently put into place are areas where you have very weak portions of the grid that you have wind and solar interconnected into, and there are stability issues for those traditional grid following inverters just to stay synchronized to the system. And so there will be tweaks to the control systems that start to approach grid forming in those areas. And there are some of those around the world. So I'll stop there, Alejandro.
Thanks so much. Okay, with this I will close this session. So I will take out the hat of moderator, and now I will start speaking as co-organizer of this workshop. Well, first of all, thanks to all our speakers of this panel. Thanks to all our speakers of the other two panels. I think this has been a fantastic workshop. It's a shame that we were not able to to meet each other in Paris this time. So, but I think we took the advantage of this, and we have a very large number of participants. So for sure we have many friends in the chat, a lot of people that have been engaged in our workshop. So I'm very happy about how this whole workshop came. Before closing, I think I would like to emphasize how important this event it is for us. Thanks for your participation. It gets a lot of insights. And for our job, we're a government-driven organization. We are here to provide policy advice and to translate technical, sophisticated topics to policymakers into concrete recommendations. So for us, this kind of workshop provides fantastic input. It's very important for our work. So we are engaged in continuing this effort. I would like to thank all our colleagues involved on the EPRI side: David, Katie, Will, Smith, Mark Wolf. On the IEA side, I would like to thank Ana Calista, Enrique Gutierrez, and Keith Everhart. Thanks so much. So with that, I will close my participation, and I will give the floor to David Hunter. David, please.
Thank you very much, Alejandro. And can I ask Will Smith to please pull up the results of the poll that we did at the beginning of this workshop, or rather the beginning of the day today. And while he's doing that, I note that we do have another poll that is open now that asks for your opinions and advice and suggestions on this workshop and what we do next year. So please take a moment to fill that poll out as well. So we asked two questions at the beginning of this workshop on related to reliability and resilience. So one is, overall, will distributed energy resources improve reliability or contribute to reliability or positively or negatively? And a majority of folks thought it would decrease the reliability of the system, although it's actually about pretty close to equally split between having either no impact or an improvement versus the percent that said it would decrease. Let's see, next slide. Our second question, which technology will increase the resilience? Which technology has the greatest potential to increase the resilience of the system? So let's see, batteries located at the transmission and distribution level was the winner, but the next two, distribution level islanding capabilities and microgrids and behind the meter batteries were fairly close followers. Let's see, okay, we're, I think, done with the slides. Before we close, I wanted to offer just a couple of comments, a couple of reflections on the workshop as a whole. So we started out on our first panel hearing about technologies, hearing about new distributed energy resource technologies, buildings, batteries, EVs, how to aggregate them. And my take home from that was that the challenge is not that the technologies aren't there. There are a lot of technologies. There are a lot of exciting new technologies, a lot of exciting new ways of using them. The challenge is going to be to figure out how to use all those technologies together. So it's how do you use your EV? How do you integrate your electric vehicle with your solar, with your battery, with your neighbors? In a way that's safe with other devices in your home. How do we fit all of that together? How do we fit that into the grid in a way that gives the grid new functionality that we don't have now? The second panel, yesterday, we heard from jurisdictions all over the world who are facing very similar challenges. In fact, I think there's a little bit of competition from different jurisdictions over sort of who's working to decarbonize their systems the fastest and who has set the most aggressive goals. And that is certainly creating challenges. It's creating a lot of challenges, but how people are addressing those challenges is quite different. So different jurisdictions are taking very different approaches to pricing, to looking at how are you going to value these new services that are going to come on? How are you going to structure the market? How will the money flow back to reward not just using electricity, so you don't just get paid for, aren't paying as you're consuming electricity, but you're paying as you're consuming electric services. Whatever those may be, and there are a lot of them. On the third panel today, looking at reliability and resilience, I think going back to the question, the poll question, will distributed resources increase or decrease reliability? And of course, we had asked that in a fairly narrow way, in which we said, will distributed resources under the existing market framework without any changes in the market framework provide a positive or negative contribution to resiliency. But I think overall I would have to go with Rob's answer. Rob Chapman said, overall, it depends. Will distributed energy resources increase resiliency? Will they increase reliability? It depends. There's a lot of potential for them to do so. There's also a lot of new challenges, new cyber challenges, new dependence on the grid, growing dependence on the grid, and getting all these things to work together. So a lot of opportunities, but a lot of challenges as well. Finally, I'd like to say that I really appreciated all of the contributions. We did have more than 520 registrants from all over the world. I was quite impressed that there were people signing in from India and Tokyo in the middle of the night and contributing their thoughts and opinions. And I think there really is a lot of similarity in how people all over the world are dealing with these issues and struggling with them. And I think we can learn a lot from each other. And of course, that's the premise of this workshop, and I think that's what we'll try to bring to you again next year. So if you haven't yet done so, please do fill out that poll and offer your suggestions for what we may do next year. Finally, just a couple of quick thank yous. I want to thank all of our colleagues at the IEA, not only Alejandro Hernandez, our fearless moderator today, but also Keith Everhart and Enrique Gutierrez, who've really provided a lot of suggestions and ideas for this workshop, as did folks on the EPRI side. Marcus Wolf has been, actually I think it was Marcus who was the original contributor to saying we really ought to do something on distributed energy resources. So Marcus, thank you for that. Particularly want to thank Will Smith and Kathy Melton for helping make this workshop run. The amount of stuff that Kathy is managing in trying to get videos to work and keep people on time and switch between presentations is while I would note, dealing with a hurricane at the same time is pretty remarkable. So thank you very much to you. And finally, the last thing I'll mention is that we've had a great relationship with the IEA. I noticed that Tom Wilson is on. Tom actually started working with the IEA 20 years ago on the Greenhouse Gas Emissions Trading Workshop, which was just held last week. And it was out of that workshop, sort of conversations there, that this workshop arose. So I will leave it at that. And thank you very much again, everyone, for participating. Kathy, you can stop recording. This will end the workshop. We will leave the chat function open for a few more minutes so folks can have any other additional comments. I think there's still actually a couple minutes left.